semester we'll mostly talk about matchings and network flows. And we start this semester talking about bipartite matching. Let's talk about matchings. Matchings. So what is it? The problem is very simple. You have a graph. Let's say something like that. So you have some undirected graph. And the matching is basically the set of edges such that no two edges share the same vertex. So we need to mark some edges, and all these edges must have different endpoints. For example, we can take, let's say, this edge and this edge. So these two edges form a matching. Yeah. Okay. Again, we pick some edges, and these edges must have different endpoints. And the problem we will solve in this lecture will be to find the maximal matching. So the maximal matching is just the matchings of the maximal number of edges. So we want to pick the maximal number of edges such as no two edges share the same endpoint. Very simple. For example, this matching has size 2, but we can make matchings of size 3. For example, if we remove this edge and mark these two edges instead. So this is the maximal matching for this graph. Sometimes we have a matching which contain all the vertices of graph. So we have matchings of size n/2, like in this case. If the matching contains all the nodes of the graph, it calls perfect matching. Not very important, but if you see the term perfect matching, it means that it is a matching of size n/2, so it contains all the nodes of your graph. Now, there are two types of this problem. One problem is for bipartite graph, and another problem is for non-bipartite graph. For example, this graph is non-bipartite. And if you have bipartite graph, you can have the same problem. So bipartite graph, you have, so you notice I split it into two parts. You have left part and right part. And you only have edges between these two parts. Like this. And in bipartite graph, it's the same problem. We need to pick some number of edges, maximal number of edges, such that all these edges do not share the endpoints. So for example, we can pick this edge and this edge. Something like that. One more? Okay, let's pick one more edge. That's all. That's the whole problem. There is a big difference between bipartite graph and non-bipartite graphs. This difference is actually quite fundamental. We will talk about this difference later in this course when we talk about linear programming and stuff. So if you look at the linear program corresponding to this problem, it's actually quite different for bipartite graph and for non-bipartite graph. So the algorithms for solving this problem is very different. Today we'll talk only about bipartite graphs. So we'll only solve the problem of finding the maximal matching for bipartite graphs. Do both endpoints need to be different for two different ends? Yes, all the endpoints must be different. Here it's not working. Okay, I see. Okay, let's remove this. Add this instead. Yeah, like this. And now we can pick this edge. Let's remove this edge. Let's add something like this. Now it's better. how the algorithms, basically all the algorithms we'll discuss in this course will look something like this. We will start from the empty matching. So first we'll pick no edges. Empty matching is a correct matching, right? If you have no edges, then no edges share the endpoint. And after this, we will add edges one by one. We will add edges by finding something which is called augmenting path. Did I spell it right? Let me check. Yeah, I think so. So what is augmenting path? Yes, we'll talk about Kuhn algorithms in just a minute. So what is the augmenting path? It is a path which looks like this. So we will find the path such that first and last vertices of this path are not used in the matching. For example, in this graph we have these two nodes are not used in the matchings. Okay. In this graph we use all the nodes, so let's change it like this, for example. So let's remove this. Let's move back to this graph. Yeah. For example, in this graph we have these two nodes. So these two nodes are free. So these nodes doesn't belong to any edge which is in our current matching. Nice. So augmenting path must have both ends in this free set. So both ends of this path must be free in our matching. Now, the edges of this path must alternate. So the first edge is not in the matching, the second edge is in the matching, this edge is not used in the matching, this edge is used in the matching, and so on. So we want to find the alternating path with both ends not used in the matching. That's the plan. So now, what we do when we find the path like this? How can we increase the size of our current matching? It was a question, yes. You're supposed to answer the questions. Yes, what we do is basically invert this path. So we remove all these edges from matching and add these edges to the matching. So we move from this state to this state. When we make the separation, the size of the matching will be increased by 1. Yeah? So here we have 2 edges in the matching. Here we have 3 edges in the matching. That's all. That's the whole algorithm. The whole algorithm looks like this. We start from the empty matching, and then we try to increase the size of the matching. We increase the size of the matching by finding an augmenting path. When we find the augmenting path, we invert all this state of all edges in this path and get the matching of size +1. For example, let's see. For example, in this graph, let's find the augmenting path. For example, in this graph, the augmenting path will look like this. So we can take this path. So this is the augmenting path. We can invert the state of these 3 edges and increase the size of the matching by 1. So how to start the algorithm? Starting algorithm is very simple. So when you start the algorithm, you have the empty matching. So in the beginning, you have something like this. all nodes of the graph are free of dimension. So how to find the first augmenting path? The first augmenting path is simply one edge. So every edge is the augmenting path of itself, right? So if you pick any edge, it is the correct augmenting path. So the ends of this path are free, and all the edges are alternates. So it's only one edge, so it's free. So you take any edge, invert this edge, like this, and now you have matching of size 1. Now you have matching of size 1, you want to have matching of size 2. What you do, you try to find augmenting path. So you find the augmenting path, for example, like this. So you find this again, augmenting path. You invert all the edges on this path. So now you have this edge, you don't have this edge, and you have this edge. So now you have matching of size 2, and so on. So each time you find augmenting path, increase the size of the matching. What's interesting? The interesting idea is that if you don't have augmenting paths, it means your matching is the maximal one. Let's prove this. So we prove that if there is no augmenting path, this the maximal is maximal. The size of your matching is maximal possible. Let's prove this. First, let's prove from right to left. So, if your matching is maximal possible, then you have no augmenting paths. This is just the size of the matching. Yeah, so M is the matching. Yeah. It's like the set of edges. So this is the size of this set. Now let's see. So if your matching is the maximal one, then you have no augmenting paths. And why is it true? Because if you have augmenting path, then you can increase the size of the matching. It means your matching is not the maximal one. Yeah. So from right to left is actually pretty obvious. Yeah? Clear enough? Again, if your matching is the maximal one, it means you cannot increase it. But if you have augmenting path, you can increase it. Yeah? So if your matching is maximal one, then there is no augmenting paths. Now from left to right. That's more interesting. Let's prove that if we don't have any augmenting paths, then our matching is maximal. Again, let's prove it by contradiction. So let's say that we have no augmenting paths, but our matching is not maximal one. Okay. Let's see. So we have our matching F, and it is not maximal. Then there is some other matching, which is maximal. So there exists some matching M max. Yeah. And the size of this maximal matching is more than the size of the M. Right? Now, let's take a look on both these matchings in the same graph. So let's draw both these matchings in the graph. So let's mark all the edges of matching M with red. And mark all the edges in M max with blue. Now let's remove all the edges from the graph, except the edges which belongs to M or to M max. What we'll have? So again, what we do? We take the graph, draw two matchings. Draw matching M and matching M max. M with red and max with blue. And now remove all other edges, which doesn't belong to M or M max. Yeah, we can also remove the edges which belong to both M and max, and it's not that important. Yes, let's remove the edges which belong to both M and max, just for simplicity. So we only left the edges which belongs to M but not M max, and edges to belong M max but not M. Now, what we have left? Let's look at any node of our graph. For each node of our graph, we may have at most two edges connected to this node. Yeah? So we may have at most one blue edge and at most one red edge. So the degree of each node in our graph is at most 2. Right? What you can tell about a graph which have degree of each node at most 2. So the degree of each node is 1 or 2. How does this graph looks like? Yeah, it may contain only cycles and chains. So if you have cycle, so let's look at the cycle. So let's have some cycle. If you have a cycle, then the colors of the edges must alternate. Yeah. So you have these edges red and not this edges red and these edges blue. Now, let's see. If you have a cycle, then the number of blue and red edges is the same. Yeah. If you have the cycle, yeah, so the size of the cycle must be even, and the number of blue and red edges is the same. But we know that the size of this M max is larger than the size M. So the number of blue edges is actually larger than the number of red edges. So there must be some component which has more blue edges than red edges. How does this component look like? It must look like this. It must be a chain like this, such that the first and the last edge of this chain are blue. Once again, the size of M max is more than the size of this M. Yeah. So there must be at least one component which has more blue edges than red edges. This component should look like this, because we only have cycles and chains. So for each cycle, the number of blue and red edges is the same. So there must be a path such that the first and last edges of this path are blue. Now it's quite easy to see that this path is actually augmenting path for the red matching. So this path is augmenting for M. No, really. So the first and last nodes of this path are not used in the red matching because we don't have any red edges going from here. So the first and last nodes are not used in the red matching. And the state of these edges is actually alternating. So we use these two edges in the red matching, but we don't use these three edges in red matching. So this path is actually augmenting path in red matching. That's all. It means if our matching is not maximal, then we must have a augmenting path. That's all. Okay, that's the whole theory behind this. So again, how we find the maximal matching? We make a empty matching, and then we try to find augmenting path. If we found augmenting path, we increase the size of the matching. If we don't find any augmenting path, it means that our current matching is the maximal one. Ta-da! That's all. Okay, now the tricky question. How I use that my graph is bipartite in this proof? So I promise you the algorithm for bipartite graphs. Cycle is even because the colors are alternating. So it's actually true not only for bipartite graphs. So in bipartite graphs, all cycles are even, yeah. But even if you have non-bipartite graph, this cycle will have even length because the colors of these edges must alternate. So. The answers, I didn't use it. So this proof is correct for non-bipartite graph as well. So for non-bipartite graphs, we will use basically the same algorithm. We will start from empty matching and then try to find alternating paths one by one until we find the maximal matching. So this scheme can be used for non-bipartite graphs as well. The only trick is how to find these augmenting paths. It turns out that in bipartite graphs, it's much easier to find augmenting paths. If you have non-bipartite graph, there is some problem how to find augmenting path, even if you have one. We discussed this problem in the next lecture, and today we'll talk only in bipartite graph. So again, this algorithm is the same for non-bipartite graphs and for bipartite graphs. The only difference is the algorithm which finds the augmenting path. It turns out for bipartite graphs it's much easier to find augmenting paths. Yes, we'll talk about maximal flows in a few lectures. Okay, that's not today. You don't need to know network flows to actually solve matching problems. Let's go. So, how to find augmenting path in bipartite graph? Well, let's see. Here we have a nice bipartite graph. So, how the augmenting paths looks in bipartite graphs. So, if you have a bipartite graph, then augmenting path looks like this. So you start from some free node in the left side, for example, of your graph, and now you need to take alternating terms. So you go to the right half using the edge which is not in the matching, and now you go to the left part using the edge from the matching. Now, this node may not be free node, right? Because we have this edge in the matching. No, again, this augmenting path always have odd size, so we cannot stop. So if we start in the left part, we must end in the right part, right? So we go to the right using free edge, then go to the left using some edge from the matching. Now we go to the right, go to the left, go to the right, and this edge from the matching, until we finally find this. Oh. So the augmenting path in the bipartite graph looks always like this. How can we use this? Let's see. We go to the right only when we have the node which is not in the matching, and we go to the left only using the node from the matching. So let's orient our edges. So let's orient all the edges not in the matching from left to right, and all the edges from the matching from right to left. So let's go here. So we orient this edge from left to right, orient this edge from right to left, this edge here, this edge here, this edge here, like this. Now we have a directed graph. What's cool about this? Now we don't need to care about if the edge is in the matching or not. So the direction of the edge actually defines the state of the edge. So these edges go to the left. That's to the left. Tuk. Now in this graph, we just need to find any path from one free node to another free node. So again, we don't care about the state of the edges, if the edge is in the matching or not. We just look at the direction of this edge. If the direction is right, then our path will be right. Okay? Well, for example, let's find some. Do we have any? We don't have any augmenting paths in this graph, right? Let's add something. So let's add, for example, this edge. So now we can find this path. So we can go here, then here, then here. So this is the augmenting path. So again, what we did, we add this direction to each. So each edge now has a direction. If the edge is not in the matching, we orient it from left to right. If it is in the matching, we direct from right to left. And now we just need to find the path from one free node to another free node. We know how to find paths in graph, right? We just spent the whole semester talking about graphs. So how to find a path from here to here? You can use depth first search or path first search. Basically, any path finding algorithm will work. So let's run, for example, DFS. So we take this free node of the left in the left part and run DFS algorithm. If this DFS algorithm will find any node in the right, free node in the right part of the graph, then we find the augmenting path, because each path from one free node to another free node is augmenting. Now, what if we have several free nodes? Let's see. So what if you have several free nodes here and several free nodes here? Now we want to find a path from one of these nodes to one of these nodes. We can simply run DFS from all these nodes. So we can iterate all free nodes of the left part and run DFS from each one of them individually. But it can be done even simpler. So what we can do, we can introduce one extra node here. Let's call it S. Connect it to all free nodes of the left part. And then introduce one node here and connect all the nodes here. And now in this graph, you just need to find any path from S to T. So if you take any path from S to T, it will look like this. So it will go to some free node of the left part, then it will go something like this. So you have this augmenting path from this free node to this free node, and then it will go to T. So in this graph, you just need to run DFS from S, find any path from S to T. If you have a path from S to T, then here you will have your augmenting path. Then you invert this augmenting path and continue again. Yes, let's like multi-source DFS. Yeah, we discussed it in the previous semester, I believe. Yes, you can do. Yes, you can use DFS or BFS. It doesn't matter. It will not affect the complexity. So let's talk about time complexity. What is the time complexity of this algorithm? Well, let's see. Each time you run a DFS, time complexity of DFS is big O of M, where M is the number of edges, right? And how many times you need to run DFS algorithm, actually? You run DFS, each time you either find the augmenting path or you don't find augmenting path. If you don't find augmenting path, it means that your matching is fine, is maximal. So you just stop. If you find the augmenting path, then you increase the size of your matching. The size of the matching is at most n, because you have n nodes here, right? The number of edges in the matching can be more than n. So you run DFS at most n times. So total time complexity will be n multiplied by m. That's all. It's called the Kuhn algorithm. Kuhn's algorithm. We will actually improve it a little bit, but the main idea is this. Very simple. Can we do it faster? Actually, we can. We will discuss algorithm which finds the maximal matching in bipartite graph faster than in n time, but not today. We need some more theory about network flows and stuff. So we'll discuss some network flows algorithm, and when we learn some fast network flows algorithm, we will go back to matching problem and we'll find better algorithm for bipartite matching, but it will be in a month, I think. Yeah, there are a lot of good heuristics which actually can improve this. For example, yes, if you just randomly shuffle all the edges and just start in random order, try to find all the edges in random order, then most of the time you will add a lot of edges to your matching. Can actually prove that if you just greasily add edges one by one, then you will add about half of the edges from the maximal matching. It's not that important, but yeah, actually there are some cool heuristics which can make this algorithm faster. But again, in the worst case, it will still work on n time. So you can build a bad taste for each heuristics, which will make your algorithm work on n time. Yeah, but there are a few improvements you can make. Now, let's actually write the code. So, how to implement this algorithm? The easiest way to implement this algorithm is the following. So, what I will do, I will run a DFS. So you can implement it just like we discussed. So you can extend your graph with these two nodes, build this direct graph, run DFS, find this augmenting path, inverse all the edges in this augmenting path, and so on. You can do it just like that. Time complexity will be like this, but it's just too complicated. There are just much easier way to implement this algorithm. You can do it like this. So what we'll do, we will not build this graph explicitly. We will just take the initial graph. So we take this graph and try to use it. So how we'll run DFS? So imagine you run DFS from some node of your graph. So let's take some node in the left part. Let's take node V. So node V is some node in the left part, and you run DFS from this node. So what happens when you run DFS algorithm from this node? You try to iterate over all outgoing edges. So let's take some outgoing edge like this. It's a node U. Now, what happens next? Let's see. This node U may be free or it may be used in the matching. So if this node is free, then you just stop your DFS, right? Then if you find this free node, you stop your DFS, you found the augmenting path. If this node is not free, then you must take the next edge you will take is the edge which connected to this node U. Okay? There is only one edge connected to this node U. It is the edge from the matching which connects to node U. There's only one such edge. So we just take this edge because we have only one edge. And go to this node. Let's put it in some array. Let's say for node U, the edge from the matching, which corresponds to node U, is actually connected to node, let's say, P of U. So P of U is the node which is connected to node U in the matching. Why is guaranteed? No, it's not guaranteed. So we will, if the node is not free, then there is one edge from the matching connected to this node. And it's only one, because it is a matching. So if we go to the node which is in the matching, then the next step will be to this node. So we have only one outgoing edge from this node. So for each node in the right part of the graph, you have only one outgoing edge. It is the edge from the matching. So what we'll do, we will run DFS like two-step DFS. So we will start in the left part. So we'll start DFS from this node V. Now we will go here and then immediately go here and run DFS from this node. So we only run DFS from the nodes from the left side. That's the whole idea. So let's run DFS of V. So we'll iterate over all edges, then go here, and then if this node is occupied, then we'll go here and run DFS from here recursively. That's the idea. Now, the second idea is actually like this. So what we need to do, we need to find augmenting path and then invert it. We can do this in the same DFS. So when you run DFS, what happens if you reach this free node in the part? It means that in the stack of your DFS, so there is a stack of DFS, yeah? So you go from here, now you go from here, you go from here, you go from here. So there was some starting node here. So you start DFS from here, and this is your current state. So all these previous states are in the stack of your DFS. We can just invert them when we go back from the recursion. So if we find this free node, then we go back from the recursion and invert the path when we go back. It will again, it will simplify the algorithm because we don't have these two steps. Yeah. We can do it like this. We can find this path, put this path into some array, then iterate over edges in this array, invert the state of all the edges. But it's too complicated. We can do it in one take. So again, what will this DFS do? This DFS will start from the node V. It will try to find the augmenting path starting from this node V. If it succeeds, then it will invert the path from this V to the free node, and then you go back and inverse the edges on the way back. Stuff like that. Yeah, clear enough. Let's see. So how this DFS function will look like? So it will return Boolean. This Boolean is true if this DFS actually succeeded. So if this DFS found the path to some found some augmenting path, so it's found some path to the free node in the right part, then it will return true. Well, let's see. Now we simply run DFS. So how to run DFS? So let's say if it's marked, then return false. Then mark. Just like the usual DFS. Then we do this thing. So iterate over all edges. Let's say U from let's say G of V, like this. So these are edges going from node V. Now we take this node U. So if this U is free, so if this U is not in the matching, how we'll see not in the matching? We'll say that P of U is actually empty. So if P of U is empty, It means this node is not in the matching right now. No, we actually don't need to. We don't need to remember about left nodes actually. Are they in the matching or not? We only need to have pointers from right to left because we only use them in this algorithm. We never use this pointer to go from here to here. We always go from right to left, so we only need to have pointers from right to left. So if U is not used, then we found the augmenting path. So we go to here and we found the augmenting path. Now we need to inverse this edge. To inverse this edge, we just need to add this edge to the matching. Yeah. So again, now we will go back and reverse this path. So we start from this edge, we need to reverse this edge. This edge must belong to the matching. So to put this edge to the matching, we just need to say that P of U equal to P now. And return true. Now, if it's not free, then we do this trick. So we go to U and then go to PU and run DFS from here recursively. If this DFS returns true, it means that this DFS found this path, already inverted this part of this path, and now we need to go back here and inverse these edges. So we need to mark these edges not in the matching, and this edge, mark that this edge must be in the matching. So we need to have, basically all we need to have is to change P of U. So we'll change P of U from this node to this node. It will make this edge belong to the matching, and this is free of the matching. So we just, again, we'll see, I'll do the same thing. You may see that we have the same thing here, so you can unite these two parts into single if statement, right? So you can say if P of U equal to none or DFS of P of U. You can simplify this, I will not. Now, if we iterate all edges and didn't find the augmenting path, we just return false here. That's all. That's the whole DFS for finding the augmenting paths. Nice. Okay, now the final trick. The final trick is the following. So, how to use this DFS? Well, we can do it like this. We can. What we need to do. In each iteration, we need to run DFS from all 3 nodes of the left part. So we need to iterate through all nodes of the left part, try to run DFS from all these nodes. If at least one of these DFS is succeeded, then we increase the matching and continue again. But we can do it even simpler. So what we can do? Let's see. For example, let's take some node. Let's remove everything here. Need some space. Let's take some node in the left part. For example, this node. Let's take some free node in the left part and run DFS from this node. DFS. Yeah. What will happen? So, if this DFS succeeded, so if this DFN finds some augmenting path, then we will invert this path and this node will no longer be free. So, if we run DFS from some free node of the left part, and this DFS found some augmenting path, then we will invert this augmenting path. This node will no longer be free. and it will always be the same. So if some node belongs to the matching, it will always belong to the matching, because the algorithm works like this. So if you mark some node, so if some node is now in the matching, it will always be in the matching, because at each iteration we just increase the set of the nodes in the matching, right? So again, what is my idea? Idea is, if you run DFS and this DFS found the augmenting path, then you no longer need this node to run DFS from, right? Because it will no longer be free, and we run DFS only from the free nodes of the left part. Second observation: if you run DFS and this DFS didn't find any free nodes in the left part, so you run DFS and it fails, it didn't find any augmenting paths. It means you have some free nodes here, but these free nodes are not reachable from this node. Now let's look at the set of all reachable nodes from this. So you start DFS from here, you will reach some nodes. So you go here, then go here, then go here, then go here, and so on. So there is a set of reachable nodes here. So these nodes are reachable from the starting node, but all these free nodes are not reachable. Yeah. Easy observation. These nodes will no longer be used in any augmenting paths. Why is it true? Well, because from this node we cannot reach these free nodes of the right part. So again, if these free nodes was reachable from one of these nodes in this green set, then they also will be reachable from this starting node, because all these nodes are reachable from starting nodes. So if we can reach from here to here, we can reach from starting node to here. Now, if from this node we cannot reach the free nodes of the right part, it means we cannot use these nodes in any augmenting paths, because in augmenting paths, all nodes of the augmenting path, from each node of augmenting path, again, augmenting path looks like this, and this is the free node. So you can reach the free node of the right part from any node of your augmenting path. So if you cannot reach from these nodes any free node of the right part, it means they cannot be used in any augmenting paths. What does it mean? It means you will never find any augmenting paths from this node. So if you run DFS from some free node of the left part and didn't find augmenting path, you no longer need to try to find augmenting path from this node. So if you run DFS and it fails, you no longer need to run DFS again. That's the whole idea. So this idea will simplify the algorithm. How the algorithm will look? We will start for iterate for all nodes of the left part. So we'll just iterate for all nodes from the left part, and try and run this DFS. So to run the DFS, let's erase all the marks. Let's fill marks with false, and run Non-DFS like this. That's all. Again, very simple idea. Again, we try to run DFS from all nodes of the left part one by one. If we succeed, we increase the matching by 1, and this node is no longer free, so we don't need to run DFS again. If we fail, it means we don't need this node. This node will never be used in any augmenting paths. So we just keep it. So again, we take each node one by one, and we either find the augmenting path or not. If we don't find augmenting path, we just keep this node and so on. L is the left part. Let's mark this. So let's say this part is L. This part is R. Yeah, true. It's actually a little bit more complicated. The graph is changing. Yeah. So when you find augmenting path, you actually flip all the edges in this path, and the graph is slightly changed. So maybe if you don't have augmenting path now, you will have it. You will have it after some changes. Actually not, because the graph only changes in the augmenting paths. Only augmenting path is changing. Not the whole graph is changing. Only the part of the graph in the augmenting path. But since these nodes cannot be used in augmenting paths, this part of the graph will never change. So you cannot reach from here to any three nodes of the right part, and this part will actually never change because you only change the augmenting paths, and this part will never be in any augmenting path. That's all. So this is the whole code of the Kuhn algorithm. I believe you can implement it just like this and it will work. Clear enough. Let's see. Ooh. I want to prove one theorem, just I don't know why, but it's kind of important theorem, but it's one of the There's one important theorem in this theory. It's called the Whole Theorem. So the Whole Theorem sounds like this. So there is a simple how's it called? A simple theorem which allows you to check if your graph actually contains the perfect matching. So let's see. We have a graph. We have n nodes here and n nodes here. And we want to check if our graph has a perfect matching. So we want to check if the size of the maximal matching is actually n. Okay, so the theorem is going like so. You have the perfect matching if and only if the following constraints satisfied. So you have, let's take any subset of the nodes in the left part. So let's pick some subset of the nodes in the left part of the algorithm. Let's say A. Now let's find all the nodes in the right part connected to this set A. So we have some edges to here and here and here and let's say here and also here. So let's say this set is n of A. It's like the set of all neighbors of the nodes in the set A. The theorem is very simple. You have the perfect matching if and only if for each set A, the size of this set of neighbors is at least the size of the set A. So then and only at n, size of maximum matching, max is n for each A. So if for each set in the left part, the size of this set of its neighbors is at least the size of this set, then we have the perfect matching. Yeah. Again, let's go from right to left. So if we have a perfect matching, then the size of this n must be at least the size of A. Why is it true? Well, it's pretty simple. We have a perfect matching. So we take the size, we take the set A. Yes, you can. The question is, you cannot implement this. Yeah, you cannot check it first. That's true. Usually you use this theorem from other ends. So you kind of use your perfect matching, your maximal matching algorithm to solve something like this. We'll do it in the practice. So yes, you usually cannot check. But yeah. Let's stop here for a second. There are two cases you can use this theorem. The first case is when you have some special graph. Sometimes you have some very special graph, and in this special graph, you can check this this theorem, but you cannot find the maximal matching first. So if you just run the Kuhn algorithm, this is in this graph, because it's very special, it will run too slow. No, it's not built explicitly. It's just some implicit graph, yeah, with some special structure. So you can simply run the Kuhn algorithm, but you can check this side of the Whole Theorem, and it will be faster than just to find in the perfect matching. Another way to when you use the Whole Theorem is something like that. You need to solve some problem which looks kind of like that. We will do it in practice. And to do this, you try to find the maximal matching. And then from this maximal matching, go back to your problem and try to solve it. Yeah? Okay. Hope it's clear enough. We need examples for this, but we'll do it in practice, not today. Now again, let's do back to the proof. So if the maximal matching have size n, so if you have perfect matching, then for each set A, the size of the neighbors must be at least A. Why is it true? Since you have perfect matching, so for each node in the A, you have some edge from the matching. So you have some edges, and these edges have different right ends. So all these right ends form a set of size at least size of A. So the size of the neighbors must be at least size of A. Ooh, nice trade. Cool. Welcome everyone. Now from the other end, I claim that if this is satisfied, then we have a perfect matching. Let's prove this. Proof is very simple. We'll see that if this satisfied, then in this algorithm, this DFS will always find the augmenting path. So just if, again, this constraint is satisfied, then every time in this loop, we will find augmenting path. So each time we'll increase matching by 1, so in the end, the size of the matching will be m. Why is it true? Again, let's see. So, let's imagine we run this DFS and it didn't find the augmenting path. Then what happened? We run DFS from here, and we find some nodes here and some nodes here. Now, I claim that number of nodes we marked in the left part is more than the number of nodes in the right part. Because let's see, so we run DFS from here. Let's say we visited these two nodes in the right part. So for each node in the right part, we have an edge from the matching. So we have edge here and we have edge here. It means if our DFS visited these two nodes in the right part, it will also visit these two nodes in the left part. So the number of visited nodes in the left part will always be more than number of nodes visited in the right part. Again, here, if we visit k nodes here, then here we visit k plus 1 nodes. Now, since we have k plus 1 nodes here and k nodes here, there must be at least one edge which is going from this set not to this set. So there must be some extra edge from here. But because the size of the neighbors of this set is more than is at least k plus 1. So we have k plus 1 nodes here. There must be at least k plus 1 neighbors in the right part. We only visited k of them, so there must be one more. So there is one edge going to here. That's all. Now basically, we prove our DFS cannot stop without finding the free node in the right part. Clear enough? Okay, hope it's clear enough. That's all. That's the whole theorem. Now, next. The next thing I want to discuss is the minimal cover problem. I need some space. Let's raise everything. I'll leave this just. Another important problem in graph theory is the vertex cover problem. The vertex cover problem looks like this. You have a graph. Again, let's draw some graph. Yeah. What you want to do is to take some nodes of this graph such that for each edge, at least one of the ends of this edge must be in this set. So you want to mark some nodes, for example, this node, and let's say this node, and this node. It isn't be complete, okay. So the problem is the following. You want to take some nodes such that each edge is covered with this set. So for each edge, at least one of the ends of this edge must be in your set. Yes, and the problem we want to find is to find the set of the minimal size. So we take minimal number of nodes, which will cover all the edges of your graph. And this problem isn't P-complete, right? It's actually quite easy to prove that this problem isn't P-complete. You can do it as an exercise. It's actually easy. So this problem isn't P-complete, but if you take a bipartite graph, this problem is actually not in P-complete. So if you try to do the same with bipartite graph, so let's say something like this, and let's say this. Okay. So if you take bipartite graph and try to do the same thing, so you mark this node, let's say this node and this node. It turns out this in bipartite graphs, it is not in P-complete. It can be solved in polynomial time. Let's do it. But before we do it, let's talk a little. It turns out that matchings and vertex cover is the pair of two dual tasks. So we'll talk about dual problems later when we'll talk about linear programming. We'll talk about what is a dual problem and so on. But let's see. So finding the maximal matching and finding the minimal vertex cover are two dual problems. What does it mean? It means they basically describe the same set, but from two different points of view. So let's say like this. So if you take any matching, not maximal matching, but any matching in your graph. So you have your bipartite graph, And you have some matching in this graph. Let's see like this. I'll just draw it like this for simplicity. So let's say you have a bipartite graph and you have some matching of this order. The size of this matching is m. Easy to see that the size of let's take some vertex cover. Let's take some vertex cover. So the vertex cover will take some nodes like this. I don't know, something like that. So these nodes are the vertex cover. Now, that's easy to see that the size of the vertex cover must be at least the size of the matching. Because you have these m edges, you need to cover these m edges. They don't share any endpoint. So all these nodes are different. So to cover these m edges, you need to pick at least m nodes, right, in your vertex cover. So the size of your vertex cover is always at least the size of the matching. Again, if you take any matching and any vertex cover, the size of your vertex cover will be greater or equal than the size of your matching. Clear enough? Yeah. But because you have this matching, you need to cover the edges of this matching. To cover all these edges, you need at least m nodes. So the size of your vertex cover must be at least m. Now, what's the interesting part? The interesting part, for dual problems, the situation looks like this. You have something like this. So you have this set of matchings and the set of vertex covers. So if you take any vertex cover, it will be greater or equal in the size of the matching. The cool trick is that for dual problems, this optimal point is the same. Because actually, what's happening that in one problem you try to maximize this thing, and in other problem you try to minimize the border, which it's hard to explain. The situation kind of looks like this. So it's like in one problem you describe the inner bound of some figure, and in other problem you describe the outer bounds of this figure. And here you try to minimize the point inside, and here you maximize the point from outside. So you will find the same point, kind of like that. If this happens, what does it mean? It means if we find any matching which have the same size than some vertex cover, it will immediately tell us that this matching is maximal and this cover is minimal. Yeah. So you don't need to prove that this cover is minimal. So if you just find any vertex cover which has the same size as your matching, it will immediately prove that the size is minimal possible. Okay, that's all philosophy. Now let's go to algorithm. So algorithm is very simple. We'll take the graph. Let's take this graph. And we will build the maximal matching in this graph, because we can. Yeah? We just learned how to find the maximal matching. Let's find the maximal matching in this graph. Well, for example, let's say this edge and this edge and this edge. Yeah. So we take the graph and build the maximal matching in this graph. Now, we do the following thing. We try to run DFS, again, the same DFS we used to find augmenting paths. So we take all the 3 nodes in the left part and run DFS from these nodes. What we will find? So we'll start from here, we'll mark this node. Now we go here, mark this node. Now we go here, mark these nodes. That's all? Yeah, that's all. So again, we start from each free node of the left part and run the same DFS we used to find our augmenting paths. So we go to the left using edges not in the matching and go to the left using the edges from the matching. We'll have the following picture, let me show you. So this is the left part of your graph and the right part of your graph. So here you have some free nodes. So you start DFS from here. Let's put, so your DFS will mark some nodes here and mark some nodes here. So let's put marked nodes here. So these nodes are marked in your DFS. And these nodes are marked in your DFS. Okay, let's call these parts, let's call this part L plus, L minus, R plus, and R minus. So plus is the set of nodes visited by DFS, and minus is the set of nodes not visited by DFS. Clear enough? So again, what we did, we built the maximal matching, and then we run the same DFS again. So we run DFS from all three nodes of the left part, and mark all the nodes which were visited in this DFS. We have a picture like this. So these nodes were visited in this DFS. These nodes weren't visited in this DFS. No. Yeah? Okay, first easy question. If you take any free node in the right part, to which set these nodes belong to? No, it's easy to see that free nodes of the left part always belong to set L plus, because free nodes of the left part are the nodes we start DFS from. Yeah. So if we start DFS from this node, we immediately mark these nodes. So free nodes of the left part will always be visited by the DFS because we just start DFS from these nodes. Yeah. If you look at the nodes, free nodes in the right part, they will be in the set R minus. So all free nodes will be here. Why is it true? Because the matching is maximal. Yeah? There is maximal matching. We don't have any augmenting path. If we don't have any augmenting path, it means we cannot move from here to here. Yeah? That's all. So all the free nodes of the left part are here, all the free nodes of the right part are here. Now let's look at all the edges. So what happened with the edges? What edges can we have in our graph? We can have edges from L plus to R plus. So we can have edges like this. Obviously, yeah, like here. We have edge from L plus to R plus. We can have edges back from L plus to R plus. We can have edges from L minus to R minus and back. No problem. What about edges from between this plus section and this minus section? What edges can we have between this plus section and this minus section? Can we have edge from, for example, from L plus to R minus? Can we have edge like this? Okay, this is question. We can have edge like this, because if we have edge like this, it means we have edge from visited node to non-visited node. Yeah, it means our DFS did something wrong. Yeah, if our DFS visited this node, why didn't it didn't go here? So we don't have edges from plus to minus. Yeah, we only may have edges from minus to plus. Yeah. Now, tricky question. Can we have edge like this? It's more tricky question. Well, it turns out we cannot have edge like this. We cannot have edge from R minus to L plus. And why is it true? Because let's look. So we have this vertex and L plus. So we have visited node in the left part. And we have this edge from here. So we visit this node, but we didn't visit this node. How could happen? So how did we get into this node? No, we didn't start DFS here because this node is obviously not free. We have this edge, so this node is not free. We didn't start DFS here. So we moved to this node from some other node here. But again, it can't happen because now we have two incoming edges to this node. So both these nodes are in the matching. And we may have only one node one edge in the matching. So if the left node in the left part is visited, then we must go from some visited node from the right. So we only may have edge from some visited node in the right part. We can't have an edge from non-visited node in the right part. So these edges are also impossible. And the only edges which are possible is the edge from L minus to R plus. So these edges are actually possible. And here we may have something like this, from L minus to R plus. Yeah, for example, here we have this edge from here to here. So this L minus, this is R plus, and we have this. That's actually quite cool picture. It's kind of this picture describes what's going on in the bipartite graph in all this matching theory. So after you build your maximal matching and run DFS, the structure of a graph looks like this. It's kind of cool to keep this picture in mind when you think about some problems about matchings or something like that. Basically about any problem about bipartite graphs. Well, that's almost all. Now let's try to find the minimum vertex cover. So which sets should we take to cover all the edges of this graph? No, it's easy to see. So to cover all the edges in graph, we just need to take a set L minus and set R plus. Let's take A minus and R plus. So if we take all these nodes and all these nodes, we will obviously cover all the edges of our graph, right? Because all the edges have one of the ends in R plus or R minus. Are you here? Why is it optimal? That's a perfect question. By now I just claimed that this is a vertex cover. Why is it optimal? We'll prove just in a second. Why is it optimal? To prove this vertex cover is minimal possible, I will just prove that the size of this cover is equal to the size of the matching. So if I prove the size of the cover is the same as the size of the matching, I will prove that it is minimal possible. That's how to prove it. Again, let's go to this picture. Let's go back to this picture. So the structure of my graph is like this. I have some matching and some free nodes here. So I have free nodes here and free nodes here. Yeah, you can prove it just by linear duality, but we didn't talk about linear duality. So I'll just prove it using very simple terms, without any linear programming stuff. So let's go back here. So what's happening? I have my vertex cover. So this is my matching. Let's say this is the maximal matching. Yeah. So I have the maximal matching and some free nodes here. let's see which vertex we used in our vertex cover. First of all, these 3 nodes are not used in the vertex cover. So this vertex cover doesn't contain any nodes, any 3 nodes from the right part and any 3 nodes from the left part. Now, let's look at the matching. So, let's prove that for each edge in the matching, we only take one of the ends of this node, or of this edge. So let's look at the maximal matching. Where is it here in this graph? So the maximal matching contains only edges from right to left, right? So maximal matching has edges like this and edges like this. But let's just mark them here. So we have these edges and these edges. So all the edges from the maximal matching are the edges from R plus to L plus or from R minus to L minus. So for each edge from the matching, we may only take one of its ends. So if it is edge like this, we take the left end of this edge. If we have edge like this, we take the right end of this edge. That's the whole proof. Now again, our vertex cover contain only nodes from the maximal matching. It may not contain any nodes from the any of the 3 nodes of our graph. Yeah? And from this maximal matching, we take only one end from each edge. So the size of this cover will be the same as the size of the maximal matching. Oh, too much happening here. Yeah. That's the whole proof. Again, the whole algorithm to find the minimal vertex cover in bipartite graph. You find the maximal matching in your graph. Now, you run the DFS from all 3 nodes of the left part and mark everything which is visited by your DFS. And now you take all non-visited edges or non-visited nodes in the left part and all visited nodes in the right part. For example, in this picture here, we take all non-visited nodes in the left part. Non-visited, there's this node and this node. And all visited nodes in the right part. So take these nodes. That doesn't look good. Because I can't run DFS again. So I run DFS from this node, I didn't mark. I also need to go here and here. Yeah, now it's better. So now again, I take all non-visited nodes from the left part and all visited nodes from the right part. So I take this node from the left part and these 2 nodes from the right part. Yeah, and now this is the minimal vertex cover. Again, why it is minimal? Because it has the same size as the matching. If I have this matching and I have the vertex cover which have the same size, it's obviously minimal. Why it has the same size? Because in this vertex cover I only take nodes from this set, and from each of these edges I only take one of its ends. So I take one of the ends from each edge from the matching, so the number of the nodes I take is the same as the number of edges in the matching. That's all. Yes, the duality is yes. The duality between vertex cover and matching is only for bipartite graphs. Yes, absolutely true. Yeah. Yes, for non-bipartite graph, this problem is NP-complete, and matching problem is not NP-complete. Yeah, so we'll solve matching problem, but it will not help us to solve the minimal vertex cover problem. That's true. Okay, I will leave this off today.